Well, hello and welcome back. We are looking at section 4.3, continuing with null space and column space. That's not going to cease. But in particular, we want to begin talking about what's called a basis. A basis is singular, bases are plural. So we're going to define what is a basis. What is a basis of a vector space or a subspace of a vector space, and bases. So the title is bases. That's plural for basis. All right, so first of all, we have to give a definition. What is a basis of a subspace of a vector space? So definition. So let's suppose you have a subspace of a vector space. Call it H. Suppose H is a subspace. Of a vector space, call it V. Remember what a subspace is. A subspace is basically a vector space that lives inside of another vector space. For example, the column space of A lives inside of Rm, right? And the null space of A lives inside of Rn. So you could say the column space of A is a subspace of Rm, or the null space of A is a subspace of Rn. So your vector space could be like Rm or Rn. All right, we want to define what is a basis. A set of vectors So we're going to use capital B for the set. So that's a capital B. It's a kind of a script B. It's not just your ordinary B like that. It's actually a script B. That's the way you're supposed to write a basis. So a set of vectors B, let's say the vectors are V1, V2, up to VP. Up to VP. So a set of vectors in the vector space V is a basis of H. So we're defining what it means to be a basis of H, provided the following criteria hold. Number one, this set of vectors, we're going to call it B, spans all of H. Spans H. So in other words, if you take any vector from H, it can be written as a linear combination of the vectors in this set of vectors B here, these guys. So anything in H can be rewritten as a linear combination of V1 through Vp. That's the first criterion. And, that's not an and, is it? And second criterion, not only does it have to span the subspace, but B has to be linearly independent. So those vectors, those green vectors, that set of vectors is linearly independent. That means none of the vectors can be written in terms of the other vectors. They don't depend on each other in any way. Oh, that's a big result, right? Really big result. So essentially what a basis is, here's a little note. What is a basis in reality? Note. Oh, it's a basis is a set of vectors. So it has to span your subspace, right? So that means you can build your subspace from it. A basis is a set of vectors that you can build your subspace from. Build your subspace from. And you want it to be the smallest set of vectors. So you want it to be linearly independent. So none of the vectors are redundant, right? None of the vectors depend on the other vectors. So you don't want any redundant vectors, so you want it to be the smallest. So the minimal set. So a basis is a set of vectors that you can build your subspace from, and it have as few vectors as possible. Have as few vectors as possible. That's essentially what a basis is. It's the smallest set of vectors from which you can build your subspace. All right, so it turns out you don't always have just one basis for a subspace. You can have multiple bases. Here's a very famous example of a basis. Let's say B consists of the vectors epsilon 1, epsilon 2, through epsilon n, and these are in Rn. All these vectors are in Rn. So you have 1 with a bunch of zeros, 0, 1 with a bunch of zeros, so on and so forth. A bunch of zeros and then a 1 for your last vector. This is called the standard basis for Rn, standard basis. For Rn. You remember what these vectors are, right? 1 with a bunch of zeros. 0, 1 with a bunch of zeros, and so on and so forth, right? A bunch of zeros and 1. So what I'm saying is that you can build any vector in Rn out of just these n vectors. Just these n vectors are enough. Yeah, so some really important results that we actually covered linear independence and spanning, right? So I mean, that's basically what we're doing right now. We're doing what? Spanning and linear independence. These are our two criteria for being a basis. You have to span a subspace, and you have to be linearly independent. So there are two really useful results. So way in the past, during our first unit, before our first exam, we had some past results, and these are very important results. So we had some equivalent conditions for spanning Rm. So if our subspace were Rm, that would be a useful statement. So we had like 4 equivalent conditions for spanning Rm. So let's say you have a set of vectors a1, a2, an. This set of vectors spans Rm. One of the conditions was, this is a really important one, if and only if. There are actually 4 ways of saying this. One of the ways was saying this set of vectors spans Rm. This was equivalent to saying that the matrix A, that consists of those columns A1 through AN, has a pivot in each row. Every row is a pivot row, has a pivot in each row. I'll put it that way. Yeah, that was really important, and that's going to be useful. Remember there was one about linear independence as well. So a set of vectors, a1, a2, an, is linearly independent, not dependent, independent. Remember, there are 4 ways of stating this. There was one last one that was really useful, though. If and only if. We're just going to state that last one. That's equivalent to this. If and only if the matrix A, which consists of those columns A1 through AN, has a pivot, and each column has a pivot. In each column. So this second criteria here, or the second result I should call it, the second result, can always be used to test for linear independence, always. Now, a lot of times we're not going to be testing for spanning Rm. Sometimes we're going to be testing for other subspaces, but anytime you're testing for spanning Rm, or you could adjust that to Rn. It doesn't matter if you use m or n. Or you could change the m to an n, just let there be the same number of rows as columns, essentially. But anytime you're testing for spanning Rm, you can use this criteria. But that is only limited, right, when you're trying to span Rm. If you're trying to span some other subspace besides Rm, you can't use this criteria. So the blue one is a little more limited because it only is available for spanning the subspace Rm. But linear independence, doesn't matter what subspace we're in, it's always going to be usable. So, two useful facts that we did way back in the past. They're coming back again to haunt us. Okay. So earlier we said that these vectors form a basis, right? Epsilon 1, epsilon 2, epsilon n form a basis. Let's actually verify that. Let's verify epsilon 1, epsilon 2, epsilon n is a basis for Rn. So the subspace here is Rn, right? Rn is the vector space and the subspace is Rn. So we're talking about a subspace of itself, right? So if you have a whole entire vector space Rn is a subspace of itself. So we're focusing on our subspace here is Rn itself. The whole entire vector space is considered the subspace. Yeah, so if you imagine, okay, out here, right, you have Rn. Well, if I can get this to work. And then inside here you have Rn, right? Rn is this guy inside. It's the whole entire dude. So Rn is a subspace of itself. Yeah, it's a subset of itself, so it's a subspace of itself because it's a vector space. All right, so we want to verify that these guys are forming a basis. So what we're going to do, we're going to make a matrix A, right? Consisting of columns epsilon 1, epsilon 2, epsilon n, and what is that? Well, we know that's actually the identity matrix, right? The n by n identity matrix, right? Which is what? 1, 0, and a bunch of zeros. No, that didn't turn out so well. 0, 1, a bunch of zeros, dot, 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 zeros, and then finally a 1. So if you look at this guy, if you look at these two for spanning, in this case Rn, you have a pivot in every row, right? And you have a pivot in every column. If you look at every single column here, right? You have a pivot going down the columns, and also in every row. So since A has a pivot in each row and column, then epsilon 1, epsilon 2, epsilon n is spans are n in this case, spans are n, because we have n entries going down the columns, and is linearly independent, Yeah. So the fact that you have a pivot in each row tells you that it spans Rn, and the fact that you have a pivot in each column tells you the set is linearly independent. So since it spans Rn, the set of vectors n, because it's linearly independent, therefore epsilon 1, epsilon 2. Epsilon n is a basis for Rn, which just means you can build every vector in Rn from those n vectors, epsilon 1 through epsilon n, and it's the smallest set of vectors from which you can do that. You don't need any more vectors than that. But if you were missing one of those epsilon vectors, you wouldn't have enough. So it's just the right size. It's the smallest set of vectors. All right, let's do maybe some more examples. Scroll a little. Exercises. Determine if the set B is a basis for Rn. Okay, number one. I have a set of vectors, B, consisting of, what do they consist of? 1, 0, 2, 1, that's my first vector. Then for my second vector, 0, 1, 0, 0. And then for my third vector, I got 0, 0, 0, 2. And I close that off. And I'm asking, is this a basis for R4? The vectors come from R4. So the question is, do they span R4 or are they linearly independent? So if one of those things fails, one of those two properties fails, then it is not a basis. So first of all, what we can do, we can observe that we only have 3 vectors, right? Remember, if you have fewer vectors than entries, then it does not span Rm, which in this case, Rm is R4. So since there are fewer vectors, only 3 vectors, right? Then entries, 4 entries per vector. Since there are fewer vectors than entries, then B does not span R4. Okay, so if it doesn't span R4, it's not a basis. Therefore, B is not a basis. Okay, so that's a quick and easy way to figure out if you don't have enough vectors. So you have 4 entries, but you only have 3 vectors. Something else. Here we go, number 2. Number 2 on the plate. Here we go. What do we got? We got B is a set of vectors consisting of 1, 2, 4, 0, and 6, negative 8. And we're seeing, is that going to be a basis for R2? In other words, can you take any vector in R2 and write it as a linear combination of those 3 vectors, and is that set of vectors linearly independent? Well, if you notice carefully, watch carefully, you got what? 1, 2, 3 vectors. So you got more vectors than entries. So since there are more vectors, 3, right, than entries, there are 2 entries going down. Then B is linearly dependent. That's an important result that we did earlier on in the semester. Really important result. So when you got more vectors than entries, your set of vectors is linearly dependent. So that violates the linear independence criterion that we needed. So therefore, B is not a basis, right? You have to not only span R2, but you have to be linearly independent. And we don't have linear independence, right? We have linear dependence instead. I should have said for R2 here. And here I should have said for R4, I believe. Okay. All right, number 3. What do we have for number 3? All right, I got B here is the set of vectors consisting of negative 1, 1, 0, 2, my first vector. Second vector is 0, 2, 1. Third vector is 3, 0, negative 1. And we're seeing, is this going to be a basis for R3? So we have 3 vectors and 3 entries. So we can't just do a cheap check and say, oh, I got more vectors than entries, or I got fewer vectors than entries. And we can't rule out one of those either linearly independent or rule out one of those spanning R3. So actually with this one, we're going to have to write it out. We're going to have to figure it out. Where is it? Okay, so I'm going to make a matrix, capital A. I'm going to do the first column, negative 1, 0, 2. It'll be my first vector. Second vector, I'll make my second column 0, 2, 1, and my third vector will be 3, 0, negative 1. And you RREF that guy, use your calculator. When I did this in the calculator, I got the 1, 0, 0, 0, 1, 0, 0, 0, 1. So that means every column and every row have a pivot. So every column and row have a pivot. Well, every row and column, I should do the row first because rows have to do with spanning, right? Columns have to do with linear independence. Every row, come on, right? Every row of A and column of A have a pivot, right? Pivot. Where are the pivots? Here, here, and here. Therefore, well, let me erase this. Let me say thus B, the set B is, I shouldn't say is, it spans R3, spans, therefore B spans R3 and is linearly independent, independent. So if it spans R3 and is linearly independent, then we can say therefore. It's a basis for R3. Therefore, B is a basis. All right, good stuff. Let's do one final example here. Number 4. What's number 4? See if I can find number 4. Here it is. Okay, I have a set of vectors B consisting of 1, 2, 3 is my first vector. My second vector is negative 1, 0, 2. My third vector is 3, 4, 4. And we're asking again, is this a subspace of R3? Not a subspace. Is this a basis? A basis. In other words, can you build R3 from these 3 vectors? And are those vectors linearly independent? All right, so you don't have more vectors than entries. You don't have fewer vectors than entries, so you can't rule out spanning or linear independence or spanning. So we're going to actually have to do this the long way. We're going to write down A as our matrix, with first column being the first vector, 1, 2, 3. Second column being negative 1, 0, 2. Third column being 3, 4, 4. RREF that dude in your calculator. Don't do this by hand. It takes too long. You're going to get what? 1, 0, 0. 0, 1, 0. And then something happens. 2, negative 1, 0. So notice that your first and second row and first and second column have pivots, but your third row and third column is a non-pivot column. So let's say note row 3 and column 3 lack a pivot. So anytime you're lacking a pivot in a row, you're not going to span R3. Anytime you're lacking a pivot in a column, you're not going to be linearly independent. You're going to be linearly dependent. So, thus, the set of vectors B does not span R3 and is not linearly independent. Is not linearly, I'm sorry, and is linearly dependent. So it's not linearly independent, which means it's linearly dependent, and is linearly dependent. So it fails on both parts, right? Both parts. Therefore, B is not a basis for R3. Yep, that's it. I'm just going to quit there, I think. Yeah, I'm quitting there. So that's an introduction to the concept of a basis. Basis, right? And remember, bases is plural of basis.